turn your scatter plot off, honestly, is press the Y equals button by itself. You see how plot 1's turned on up there? Put your blinker on top of it. Press enter, and now it's off. Now if you press graph, all you'll see is your curve.
It's not off.
Press enter.
I did.
Now arrow down. It should be off now.
Go to Y, or go to your graph.
Oh, you cleared out your equation. You have to go on top of plot 1 and press enter like that. Yeah, now we need to get your. We now need to get your model back though. There. Well, she touched it just in the wrong way. That's all. That's all.
A bad story in my life.
So here's the deal. I'm going to write our model up on the board. This is the model for Sean's speed, for Sean's distance as a function of time. Here's my distance as a function of time, and I'm going to round off the decimals. There's a lot of decimals in this model, and I don't think it's worth writing them all out. I get y equals about 1.24 x squared plus 1.17x.
Putting that y2?
No, I'm just writing it down on the board. We're going to keep it up here for reference as we work through. We're leaving y1, y1. Y 1.17x minus 1.35. Graph. Now remember what that is. What is x and what is y? What is x and what is y up there? X is something and y is something. X is time, y is feet. Yes. X is time in seconds. Y is distance in feet. And this goes all the way back to one of the first questions that Nick and Di asked earlier today about the how do you know what?
Go ahead.
No, you say that.
How do you know which order to put these in?
Answer that question. How do we know that x is time and y is distance?
Because where we put it in one zone.
Because we made it be that way.
With our...
We defined it to be that way. And this happened, a couple of you guys actually put them in backwards. You put the time in y2 and the distances in y1, and you can run a regression on that, and it's called the inverse regression. You actually get a parabola that looks like it's laying over on its side, because it has to be. It's essentially the same thing as doing this. Oops, sorry, like this. You get an inverse of it. But we don't want that. We want distance as a function of time, not time as a function of distance. Because the reason why I do it this way is because that's what we actually talk about. When you look at how fast you're going in your car, like when you see that sign on Business 97 or 97 and it's flashing 48, you're like, crap! You look down and you look at your speedometer and you see how fast you're going. What unit is your speedometer kicking back at you? Assuming you're not in Canadian, eh? What unit is it coming back at you at? Miles per hour. This is the same thing, except it's feet per second. Because I wasn't going fast. We'll figure out miles per hour by the end. We'll do a conversion at the end to figure out how fast I was going. But it's feet per second, so it's distance over time. And that becomes the rate. The rate is distance over time. We're used to having time as an independent variable, just because of how we are. Because we're always timing things. How far did I get in this amount of time? How fast do I have to run to get this speed, and so forth and so on and so forth. So that's why I like putting time as the dependent in the x variable. Di, it's a great question. Does my answer make sense?
So far.
Okay, good. Thank you, my friend. Now, Crystal, I want to address your concern look from earlier. This was a great one. As soon as I said I'm going to use the linear to talk about the quadratic, you're like, dude, the hell with you. Here's the deal. Why? Why? Stick with me. Stick with me. Because that hairdryer that the police use, and that those automated solar-powered speed monitors use are not using quadratic. They're using linear. Watch me. Work with me here. Work with me here.
All right.
First things first. I want to talk about something. And we're going to shorthand it because we're going to write it a lot over the next 45 minutes together, maybe even into Wednesday. I want a phrase called average rate of change. We're going to shorthand that because you're getting tired of writing very quickly. But the first thing I want to do is I want to talk about why we care about it. Okay? I want to talk about how why we care about it. So let me ask you a question. How fast was I going right there? Now I know I had you estimate this. I said write down an estimate of how fast you think I was going. I actually posted it on Facebook with the graph. I put that graph on Facebook. A bunch of my friends were like, pretty damn fast. But nobody threw out, somebody put 88 miles per hour. It's a great Back to the Future reference. I love that. But nobody actually threw a guess down because it's kind of hard. Even after I put the video link up, I put a short snippet of a video of me writing down, coming towards the camera. So you saw me kind of go by. But still, nobody put guesses on after that. Because it's hard to do. It's hard to kind of estimate. I'm sure that you guys, give me some speeds. How fast?
33 miles.
35?
33.
33? 15? 15? Very disparate. 30s to 15s. 18? Wide range. It's hard. 10. It's hard to estimate those kinds of things. It's hard because, first of all, you guys at the end are going to get a skewed version past the guys in the middle. Because I was going faster at the end than I was in the middle, wasn't I? You guys at the very beginning saw me at the very beginning when I was struggling to stay vertical. By the end, I had no problem staying vertical. But I go by so quickly, it's hard to... So what we have to do is, we have to talk about how fast I'm going at that moment. The problem with that is, you have to take an infinitely quick snapshot at that moment, and you can't do that. You can't do that. Here's why. What is the average rate of change? Here's the mathematical definition of it. It's defined as total distance over total time. That's the magical formula. And it's not magical at all. It's not magical at all. It's very, very simple. Distance over time. Total distance over total time. Does that sound familiar? It should. What is it? It's rise over run is all it is. It's something you already know. This is why I want to use it, because you already know it. But you don't. Hey, Sean, I trust you. Thank you for trusting me. I will not let you down, my friend.
I'm sure.
Here's the
This might
kicker.
take a while.
It will. It will, because I want you to understand it well. I can show you a quick calculation with no understanding of what's going on, but I don't want to do that.
Yeah.
I want to make sure it is understood.
Yeah.
The problem with this is, you can apply average rate of change at any point between any 2 points on any curve. So, first of all, can we agree on a shorthand? Can we call it AROC?
Yeah.
Average rate of change. Well, we're eventually going to have IROC, instantaneous rate of change.
Okay.
Also a really, really funny car from 1982.
Yes.
Really good. But we're going to call AROC for average rate of change. Now, when you specify average rate of change, you have to pick two. You guys said it was slope, right? You guys said it was slope, total distance over total time. I totally agree with you. I totally agree with you. The kicker is you have to specify then how many points. How many points do you have to specify if you want to use a slope?
2. Well, yeah.
Don't you? Don't you have to use 2 points?
Yeah.
Because to get the right, I wish I hadn't erased it now, but up here in that top corner,
Y2 equals Y.
I had y2 minus y1 over x2 minus x1. Those 2's and 1's are important because they imply that you have 2 different points. So here's the deal. Let's figure out some average rates of change for my entire trip. Okay, so here's what we're going to do. Let's just jump right into it. I'm going to come over to here. I think we're going to need more board than what's over there. So let's put this up. We don't need the Excel spreadsheet, I don't think, anymore.